and some preliminaries. Okay, so the first is about the which is about the set. So we should have some conventions for the notations for the sets. Okay, we have. So in general, we will use a capital letter to denote a set. Okay, so we use capital letter, use A or B or C, capital A, B, C, something like that, capital letter to denote a set. Okay. And we use this symbol X. This symbol to denote it belongs to. Okay, it belongs to the set A. So this means X is a member in A. And we use this symbol X. We have the slash A. That means X is not a member or element in A. Okay, and if we use A equals B, that means these two sets are exactly the same. They have the same elements. Okay, and we always describe a set using the following ways. That we say A is, how to describe the set? We use X represent the elements inside the set. Okay, and this X should satisfy certain conditions, which is the statement about the statement about this X. Okay. Statement about X. So such as the X should be less than 100 or something like that. Okay. So we also have some relations between two sets. And we say that A, using this symbol, that means A is a subset of B, which means all the elements in A must be in B. Okay, so we use this symbol to denote. We use this symbol to denote the subset. Okay, and both sides of the symbol must be a set. Must be a set. Okay, so of course, if you use this way, the same thing. B, they are the same thing. Okay, A is a subset of B. And we have some operations on two sets. A intersects B. Okay, so that means what is the common part of these two sets? If we use the Venn diagram, this is the set A and this is set B. So the intersection would be the common part. Okay. So if we use the braces to describe the set, this would be the element X such that satisfy the following conditions. X is an element in A, belongs to A, and X is also an element in B. Okay, this means the intersection. And the union, A union B. So that means we put together the set of A and B, okay? So if we use the Y diagram, that would be, this is set A, the set B, that would be the whole thing. Okay, so it means if we use this notation, X is an element such that the element in this set such that this X is in A or X is in B. Okay, so we also have another one, which is B slash A. That means we read as a B minus A. Okay, B minus A. Sometimes you will see it will look like this one, B minus A. They're the same thing. What does this mean? This means we use the Venn diagram. So the element in B, but not in A. This is the A, this is the B. Elements in A, but not in B, which is here. Okay. So, which is the set of X such that X is in B, but this X cannot be in A, does not belong to A. Okay. And we use if A is equal to this symbol, this means this A is an empty set. Okay, so there is no elements inside. So what is the empty set? Empty set is this one. This is called empty set. We have two braces, but nothing inside between. Okay. Okay, so this is about sets. Let's look at another one, which is about functions. So we are given two sets, given A and B. And a function is some relation between these two sets. It will associate with each element in A. Okay, so this is a function, F. We use F to denote a function from A to B is a relation or correspondence that associate with each element in A. Associate with each element or sometimes we call it point in A, an element in B. Okay, associate with each element in A and element in B, in the set B, or the point in the set B. Okay, so we denote this way, denote this function by, sometimes we write it this way, F is from A to B, which is defined by if the X is the element in A, okay? So this function f, it will have a corresponding element which is called f of x in B. Defined by this way. So we will f will map x to an element f of x in B. Okay, so this x is in A and this f of x is in B. So here is the graph we have. So this is if this is set A and this is set B. Okay, and then we have element x here. We use this function fx f. You will have a new element which is called f of x in B. This is the relation. Okay, we set up the relation between two sets using this function f. Okay, and this A is called the domain of f. So each element in A you must have some image, okay, in B. So this A is called the domain of f. Sorry, of f. And B is called a codomain. Okay, B is called a codomain of this function f. What about all the images of this set A? Okay, so for each element in A, we have some image f of x in B. What about all the images? Okay, if the elements run through this whole set A, then you have many elements in B, right? The collection of these elements is called f of A. F of A. This is called the range of the image of F. Or the range of F. Okay. So how do we define it? Define is the f of A is a set, which is the elements we denote by y in the set. This element should be equal to of f of x. This x is any x in A. Okay, so x runs through this A, then you have different y's for each x, right? Then you collect this y, then you form a set which is called f of A. This is called the image of this f. Okay. And so here let's look at what is the f of A, and we use this color. So in general, this is f of A should be a subset. This is the f of A. This is f of A. F of A should be a subset of B. Okay. So here is the things f of A should be a subset of this codomain B. So when we talk about something like about the functions, we also need to talk about some special functions. The first special function, which is called onto. Okay, a function is onto. What's the meaning for the function is onto? So onto means the image of f is equal to the set B. Okay, onto. So all the set B would be the range or the image set of function A. Okay, so this is the function f. Sorry, let me use another color. When f of A, this is the image of the range of this function, is equal to its codomain. Right? This is called a format. then this function is called, f is called onto function. So in other words, or any element in B, you must have a pre-image, okay? A pre-image element in A. For all the function, for all any elements in B, you must have the pre-image for this function. And another one is function is, so this is the one thing, 1, 2. This is the function, f is 1 to 1. What does this mean? 1 to 1. So we will use this symbol to denote 1 to 1. Okay, so 1 to 1 function. 1 to 1 function means for any, we use this symbol. It's like a upside down triangle. Okay. We use, I put it here. So this kind of symbol we often use in your proof. This one means for any. Okay. For mathematician, we don't want to write many words, right? So we always use some symbols. We use this one. This means there exists. There exists. We use this symbol. Means there exists a unique one. A unique. Okay, I have no space. There exists a unique one. Okay, so let's go back to our one-to-one function. So one-to-one function means for any y in f of a in its range, there exists a unique x in A. Such that we use s dot t. Such that st means such that y is equal to f of a, f of x. Right. This is called a one-to-one. Right. If you have two sets, a and the f of a, if this is a, this is the f of a. Okay. And one-to-one is for any element in f a, which is called y, there is only one element in A corresponding to it. So this relation F. Okay, so this is a one-to-one. And this would not be one-to-one. You have more than one corresponding to it. Right, this is not one-to-one. Okay, so then the next one, which is about the invertible. We say that f is invertible. That means the inverse function exists. If and only if this function is 1-to-1 and onto. Okay, so this is a 1-to-1 correspondence, and the codomain is actually the range. It's called a format. Okay, this is called the invertible function. So in other words, if f is given by from a to b, if this is the function f, that means for any value, any number, or any element y in b, there exists an x in a such that y equals f of x. Okay, such that y equals f of x. So this is called 1-to-1. So this b is our image. Okay, is the range, not just the codomain. Is the range exactly. Okay. So how do we define this x? It says for any y, the y is given. There must be a function, must be an element x in A corresponding to it. Through this relation, how do we do that? What is x? So we denote x by x is equal to f. This is called inverse, f inverse of y. Okay. So what is f inverse? F inverse is the relation, is a function from B to A. Okay. And this f inverse is called the inverse function of AF. Okay, so this is the in this course we will only deal with the real numbers. Okay, we will only deal with the real numbers. So we use this one to denote the set of all real numbers. This R is the set of all real numbers. Real numbers. Okay. So next we want to talk about some axioms that this real number set should satisfy. So axioms means something we just take it without any proof. Okay. So this real number set should satisfy 3 groups of axioms. Okay, let's look at the first axiom, which is called the field axiom. This is the first axiom. Field. For the field axioms, we should introduce 2 operations on the real number set, okay, on this real set. We should introduce 2 operations on R, on this real number set. These 2 operations, one is called the addition. Another operation is called the multiplication. then these two operations should satisfy the following axioms. So let's look at the axioms one by one. The first axiom, which is called the commutativity of addition. Commutativity of addition. Which means for any, I can use a symbol. For any A and B in the real number set, A plus B is equal to B plus A. Okay, we just take it. This is called an axiom. We cannot prove it. We just assume it should satisfy this one. Okay, this addition should satisfy this condition, which is called the commutativity of addition. Next one is the associativity. Associativity of addition. So first, let's just talk about the addition. Okay. So that means for any A, B, and C, three elements, for any three real numbers, A plus B, then plus C equals A plus B plus C. Okay, so yes, we can put the parentheses as we want. The third axiom is about the additive identity. So this is the for any, what does this mean? For any A in the real number set, there exists a real number denoted by zero, such that 0 plus A is equal to A plus 0 equal to A. So this 0 is called the additive identity. Okay, A plus any number, real number A plus 0 equals 0 plus A. This is the commutativity, right? Commutativity, and equal to A. Okay, so this, you plus 0, it will not change anything. So this is called the additive identity. The next one is called the additive inverse. What is that? The additive inverse must exist. So that means for any A in a real set, there exists an element B in the real set such that A plus B is equal to the additive identity 0. Okay, so these 4 axioms is for the addition operation. Okay, is for the addition operation. So the addition operation should satisfy these 4 axioms. So now let's look at the next operation, which is called multiplication. So the multiplication also should satisfy other axioms. So the first one is the similar one, which is the commutativity of multiplication. So that means for any A, B real numbers, A times B is equal to B times A. Associativity of multiplication. Associativity of multiplication, which means for any A, B, C to be any 3 real numbers, A times B then times C is equal to A times B times C first. Okay, you can put the parentheses anywhere you want. The third one is called the multiplicative identity. So we have the additive identity, so we also have some multiplicative identity. Identity. So for any real number A, there exists a real number we denote this real number by this, denoted by 1, such that A times 1 equals 1 times A equals A. It will not change the original number under this operation. Okay, the previous one, which is called 0. 0 is the additive identity. On the addition operation, it will not change the original number A. Okay, you add add 0, it will still be A. For the multiplicative identity, you multiply by 1, it will still be A. Okay. Then we also have the multiplicative inverse. Multiplicative inverse. So that is for any A, a real number A. So here, A is not 0, is not the additive identity. There exists B, the set R, such that A times B is equal to the multiplicative identity. Okay, so this is called the multiplicative inverse. You multiply this number of the multiplicative inverse, it will recover the multiplicative identity, the similar one for this additive inverse. If you add this additive inverse on the real any number A, it will recover the additive identity. Okay, so this is the 4 axioms about the multiplication. So the multiplication operation should satisfy these 4 axioms. We have more, 2 more. This is the distributive property. Distributive property, which means for any 3 number A, B, and C, 3 real number, A times B plus C is equal to A times B plus A times C. Okay. The next one is called, we have the non-triviality assumption. That means we should have the multiplicative identity 1 is not the same as the additive identity 0. Okay, they are not the same thing, so we use the different symbol. Okay, and this 1 is not the 0. The 0 is called the additive identity, and the 1 is called the multiplicative identity. So these 2 numbers are not the same thing. Okay, so these 10 axioms is called the field axiom. Okay, so this real number set we will talk about in our course should satisfy these 10 axioms. This is the first axiom, which is called the field axiom. Okay, field axiom. Of course, we have more. We will introduce later. So now let's look at remarks for this field axiom. So the real number system should satisfy 3 groups of axioms. So this is the first group, which is called the field axiom. Let's look at some remarks. The first remark, which says the additive identity 0 is unique. Identity is unique. We only have 1 additive identity 0. So the next question is why? Right? So we should, when we study this course, you always ask yourself why. Right? We try to prove it. Okay, so now let's prove it. We only have 1. So the format of the proof, the first, you must write down the proof. This word, proof. Okay. And we suppose we have, which is called 0 prime. We use another letter, okay? Another symbol, 0 prime. 0 prime also has the property, the following property. 0 prime plus A is equal to A plus 0 prime should be equal to A for any A, any real number A. Okay, so we assume this 0 prime is an arbitrary additive identity. So we want to show that this 0 prime must be the 0, right? This 0 we already know it exists, right? It exists in the additive identity axiom. Okay, we must have this 0. So now we have another one, 0 prime. So if you can prove this 0 prime must be this 0, then we are done, right? This is called a uniqueness. Okay, so we assume this 0 prime also has this property. So that means this 0 prime is another additive identity. It's an additive identity, right? But now we need to show that we need to show that this 0 prime must be 0. So we have no other tools. The only tools we have is the axiom. Okay? So now we just play around these 4 axioms that try to prove this result. So we know that, so here is 0 prime satisfies this condition, right? A is any real number. And we know this 0 is also a real number, right? So we have, if we replace A by 0, you will have, in particular, zero primes plus 0 is equal to 0, right? This is just from this one. You replace A with 0. So 0 primes 0 equals 0, right? You replace A with 0. So you must have 0 primes, 0 prime plus 0 equals 0. This is the properties that 0 prime has. On the other hand, by the definition, of the additive identity 0, what's the definition of 0? 0 plus any real number would be that number, right? So 0 prime plus 0, of course, equal to 0 plus any number would be 0 prime. In the first one, we treat this one as the additive identity, right? This identity, additive identity plus any number would be that number. So now we still use this expression, but we treat this 0 as the additive identity. Because we know this is the identity, additive identity already, right? This 0, we denote that additive identity by 0. So this 0 plus any number would be that number. So you compare these two. Since these are the same, the expression are the same, right? For the left side. So you can conclude that 0 prime is equal to 0. Okay. So when you complete the proof, draw a box and shade it. Okay, so this is the first proof we have in our class. So now let's look at the second remark. The second remark is A multiplied by 0. Of course, we know, according to the commutativity of the multiplication, it's equal to 0 times A, right? So now we want to prove it's equal to 0. We have no this result yet, right? 0 multiply anything equals 0. We don't know why, right? This is the thing we want to prove. So let's prove it. So we note that since 0 is the additive identity, so 0 plus any number, we take that number to be 0. 0 plus 0 would be 0, right? We take a to be 0, right? So 0 plus a equals a, so 0 plus 0 equals 0. Then we multiply a number a on both sides. Okay, we multiply a on both sides. Then we can use the distributive property. This is equal to a times 0 plus a times 0 equals a times 0. Okay, so any number, any number must have the additive inverse, right? For any real number must have the additive inverse. So now let's add the additive inverse of a times 0. This is a times 0 is a real number, right? So we added its additive inverse on both sides. We add the additive inverse of this real number. This real number is formed by a times 0 to each side. So if you have a number, you add its additive inverse, then it would be 0, right? A number plus an additive inverse of that number would be equal to 0, right? This is the axiom we have. So if you add the one additive inverse of a times 0, so that would be, if you add this one, add an additive inverse on both sides, then this would be 0. This would be 0, right? So then you have a times 0 equal to 0. So since we can use the commutative property that, so also we have 0 times a equals 0, because a times 0 equals 0 times a. This is by the commutative property. Property of the multiplication. Okay. So we've finished the proof for this part. So a times 0 equals 0 times a equals 0. So now, after proof, we can use the result. Okay. So in this course, you can use the result we proved in our class. You cannot use any other result. If you use other result, you should prove it first. Okay. So this is the second remark. The third remark. For A, B, any two real number, A, B, if A times B equals 0, then A equals 0, or B equals 0. two numbers take the multiplication equals the additive inverse, additive identity, the multiplicative identity, 0. Sorry, yeah, it's the additive identity 0. Then this one of the number should be, at least one of the number should be the additive identity 0. So now let's prove it. So we consider two cases. The first case, case 1. A equals 0. If A equals 0, okay, we're done, right? The result is A equals 0 or B equals 0. So if A equals 0, so it's done. So the second case, case 2. We should consider all the cases, right? The first case is A equals 0. The second case is A is not 0. Right? This is include every situation, right? These two cases include every situation. So now we need to show that we need to prove B equals 0. If we can prove that, then we're done, right? So we let D, letter D, be the multiplicative inverse of A. Multiplicative inverse of A. So that means i.e. D times A equals A times D equals 1. Right? This is called the multiplicative inverse. If you multiply this number, its inverse, it would be the multiplicative identity 1. Right? So since continue, so this is the we introduce a letter D, which is the multiplicative inverse of A. So we know that since A times B equals 0, this is a given, right? Then we multiply D on both sides. We just prove the result. A real number times 0 must be 0, right? So it's equal to 0. So D times A times B equals 0. Okay. On the other hand, let's do a little bit change on this expression. We use the associative law or associativity axiom, which is equal to D times A, then times B, right? D times A is what? D times A, we know, we assume D is the multiplicative inverse. So D times A is equal to 1. This is 1 times B. Then we use the axiom for the multiplicative identity. 1 times B equals B. So compare this. D times A, B is equal to 0. D times AB equal to B. So we have B is equal to 0. Okay. So this is finish the second case, and we finish all the cases. Let's look at remark 4. So this is for the multiplicative identity and the multiplicative inverse, right? So now let's look at another one, which is the additive inverse. The additive inverse B. This is the letter we used in our axiom. The additive inverse B is unique. So this is a really important result. Why? Because if you can prove that, you also proved this result. A plus x equals 0. This x is called the additive inverse, right, of A. If you can prove the additive inverse B is unique, so that means this equation has a unique solution. Right. This equation, this x should be the additive inverse, right? Because you add A, then it becomes the additive identity, right? So this equation, if you can prove the additive inverse is unique, that also means you proved this equation has a unique solution, right? So now let's look at how to prove it. So we suppose, since it's the uniqueness, so we should prove for the uniqueness, there is a typical strategy we have. We should assume there is another one, right? Then we try to prove that one should be the one you already have. There's no other choice, okay? So suppose we have a B prime, which is a real number, satisfies A plus B prime equals B prime plus A. This is the commutative law, right? Equals 0. So this B prime is from this identity, from the definition of the additive inverse. So this B prime must be an additive inverse, right? So next, we want to show that this B prime is the B we already have. We need to prove, or need to show, this B prime is equal to this B. The B we already have. Okay. So now let's look at how to do that. So B prime is equal to B prime plus 0, right? 0 is the additive identity we already have. So any number plus 0 should be that number. So B prime equals to B prime plus 0. And 0, we know B is the additive inverse of A. So 0 is equal to A plus B. Okay. Then we use the associative axiom. So we group B prime plus A first, then plus B. Right, this is the associative axiom. B prime plus A. How do we assume B prime? B prime means A plus B prime equals B prime plus A should be equal to 0. This is the assumption we already have, right? So this would be 0 plus B. And 0 is the additive inverse, additive identity, plus B should be B itself. So you can see we prove that B prime is equal to B. Okay, so this is we finished the proof. So now let's denote two things, okay? This is another remark, the remark of the remark, okay? Yeah, the remark for this proof, this result, the additive inverse is unique. So we denote the additive inverse of A by negative A. So we use this symbol, which represent the additive. We add a small line in front of this letter, right, to denote the additive inverse of A. We not use B anymore. Okay. So from this letter, this is the second remark for this result. Okay, the first remark is we use a symbol which is called negative A to denote the additive inverse. The second remark, which is with this one, we can define the difference, the subtraction. Okay, let's define the difference. So far we know in the real number system, we also have another operation which is called subtraction, right? But at the beginning, we only have two. We only introduce two operations, addition and multiplication. Addition satisfies 4 axioms, and multiplication also satisfies for another 4 axioms, right? So now we want to use these two operations to introduce another one, the third one operation. The third operation is called the difference or subtraction. The difference we denoted by A minus B, okay? How to define this difference? We use in the following way, by the following way. A minus B. This symbol means it's defined by the right side. Okay, what is A minus B? A minus B is actually A plus it's the additive inverse of B. This is called A minus B. A minus B is actually A plus the additive inverse of B. Okay, the third one, C. So what is A minus A with this definition? A minus A is equal to A plus the additive inverse of A. A plus the additive inverse of A is equal to the additive identity, right? Which is 0. So A minus A is equal to 0. Okay. So we stop here.